This is Shetty from UW-Madison. I'm going to talk about our work on predicting the nonlinearity in the TMD benchmark structure using QSMA and SICE. A quick overview of the TMD structure. It consists of a thin curved panel that is clamped at the ends using bolts. The bottom block, which is known as a support, is mounted on a shaker at the back. There are 6 bolts on each side that are used to hold the panel in place, and they are arranged in 2 rows of 3 each. Now the curved thin panel results in geometric nonlinearity, and there is friction nonlinearity at the contact surfaces that are held together using bolts. Our aim is to predict the linear frequencies of the first 5 modes and the amplitude dependent frequency and damping of the first mode. Now a quick overview of the modeling approach that was used and the linear analysis results. So we first started with a simple 3D model of just the panel, and this was done in order to check mesh convergence. So we were varying the mesh size to identify when the element size does not significantly affect the linear frequencies. We used solid tetrahedral elements, and it was observed that reducing the global mesh size from 5 mm to 2 mm only changes the frequency of the mode 1 by 0.08% or less than 0.1%. Therefore, 5 mm was considered sufficient mesh size. Hence, the uncertainty in the first natural frequency is estimated to be a few tenths of a percent, and the uncertainty in higher frequencies was found to be 1 to 2% due to mesh convergence. Now, the 3D FE models were built with gradually increasing complexity. So we started with just the panel, then the supports and blocks were added, but the bolts were left out, and there was no contact defined at the surfaces either. Next, the bolts and contact were also added. Fine mesh is needed to resolve the contact pressure distribution, which necessitates a finer mesh than would be desirable in other locations. As we go on increasing the complexity, the computational cost also increases, even for a linear analysis. Therefore, we need a simpler, faster model, especially to be able to study contact. So we considered a 2D finite element model. This comes down to 5 rectangles basically. You have 2 rectangles that are representing the support, then you have this representing the blades on top, and you have the panel which is represented by a long, slender rectangle. Now the bolt geometry or the holes were not considered, and instead the preload was applied as a line pressure. The equivalent pressure can be calculated as an average preload force acting over washer areas plus 0 force acting over the rest of the area across the depth. The panel is modeled as flat, and the preload step causes it to bend. The contact is defined between the surfaces using Coulomb friction. Now we're assuming here that the cantilever stiffness is high enough for the support to behave rigidly at the bottom. This is why the stiffness due to the cantilever nature of the support is neglected. We'll show later that it can be proved to hold true using the 3D model. This model also allows for a much finer mesh at the contact region, as seen in the figure here, to better capture microslip behavior, that is, slips occurring due to friction. Now, the table here shows the linear modal analysis results from the 3D model as well as the 2D model. A few notes about this. The 3D model includes the bolt geometry details, but it does not include the stress in the panel due to the curvature. The panel was modeled already being curved. The 2D model, on the other hand, includes the stress due to curvature, but the bolts are modeled as a simple line pressure load. The 3D model was also analyzed with the fixed boundary conditions at the base of the support to replicate the 2D model boundary conditions, and it was found that the change in frequency estimates was negligible. This is why we're assuming that our 2D model assumptions should hold true. Therefore, at this point, our best estimate of the natural frequency is from the 3D model, and the uncertainty that arises due to the discrepancies in the two models is equal to the percentage difference between the two frequency estimates. Now, this does neglect one important source of uncertainty, any deviations of the panel from the nominally flat geometry. Additionally, uncertainty of material properties is also yet to be considered. Now let's talk about our nonlinear analysis. We're using QSMA or quasi-static modal analysis to obtain the restoring force backbone curve. In QSMA, a static load is applied to the structure in the shape of the mode that you're interested in calculating the nonlinearity of. The corresponding deflection with all the nonlinearities active is calculated from the finite element model, and then this can be done over the amplitude range of interest to get a restoring force backbone curve similar to something that is shown over here. So we can use QSMA to get the restoring force backbone curve, but now how do we calculate the frequency and damping from this backbone curve? We're going to look at it in two parts. Let's start with geometric nonlinearity. Geometric nonlinearity affects the stiffness of the structure, and Park and Allen showed that a QSMA-based STOF ROM can accurately capture the strongly nonlinear behavior that is observed due to geometric nonlinearity. So a quasi-static response is obtained using the finite element simulation, and then using this method we can fit a polynomial stiffness term to the curve with the help of least squares. The resulting STOF ROM is dubbed the SICE ROM. And now any NNM computation technique like the pseudo arc length continuation method can then be used to estimate the frequency behavior due to this SICE ROM. So geometric nonlinearity can be easily characterized using QSMA and SICE. Now we also have to look at friction nonlinearity. Bolts are a significant source of damping and stiffness change in built-up structures. Friction between bolted surfaces causes the frequency and damping to change with vibration amplitude. At low amplitudes, the regions that is closer to the bolt remain stuck, but the ones that are further away from the bolt, they start to slip. This is known as microslip. And in the microslip region, there is a small change in the frequency and orders of magnitude change in the damping that is commonly observed. So using the backbone curve from QSMA, we want to be able to estimate this frequency and damping change due to the bolts that are present in our structure. Now, friction nonlinearity is hysteretic in nature, and we can apply Masing's rules to obtain the complete hysteresis loop at any load amplitude. According to Masing's rules, if you have the loading backbone curve, we can obtain the displacement in the unloading region as the displacement at the reversal point minus twice the total function that represents this backbone curve. By extension, the reloading is just the negative of the unloading and a mirror of the unloading, as you can see in this figure here. The equations for Masing's rules can be found in the reference mentioned below, reference number 1. Once we get the loop, Lacayo et al. Also showed that the change in stiffness can be calculated as the secant of the curve, given by this equation, and for damping, the dissipation can be calculated as the area inside the loop, and the damping ratio is calculated by assuming an equivalent viscous damper. Assuming the two nonlinearities can be isolated, we can represent the total nonlinearity as a parallel arrangement of the Masing model and the SICE ROM, given by the equation of motion shown here. Now, the use of ROMs is expected to be computationally efficient because we only have to perform quasi-static analysis to obtain the backbone curve, and then we fit the ROMs to it to get the frequency and damping estimates. However, we need to know how to isolate the two nonlinearities. Our idea for doing this is to perform two quasi-static simulations. First, we perform QSMA with rough friction setting in Abacus, so there is no slip at the interfaces, and there's only geometric nonlinearity. The resulting force displacement curve is given by the blue line shown here. Then we change the contact condition to include slip, so mu is equal to 0.6. Now we have both geometric and friction nonlinearity. And if we were to subtract the two curves, assuming there is no interaction between the two nonlinearities, we would get the nonlinear force just due to friction. Now the negative slope of this resulting curve is due to the decrease in frequency that is caused due to friction. Now we're going to look at the results that we get by applying this approach. First, we use the 3D models of just the panel and the partial assembly to study geometric nonlinearity and see what kinds of results we get. Only a small difference can be found between the panel and the partial assembly. This means that the boundary conditions are rigid enough and have negligible effect on the nonlinear response. Now we also observed relatively weak modal coupling between modes 1 and 5, and going forward we assumed it is safe to neglect modal coupling. Now the third order SICE ROM is already able to capture the static nonlinear behavior quite well, and the accuracy goes on increasing as we use higher order ROMs. We will be using fifth order SICE ROMs for all further analyses. Once we get the SICE ROM, the amplitude dependent frequency is calculated using shooting and pseudo arc length continuation method. Now the SICE approach, as we can see, is able to quickly capture the main backbone curve seen in the previous slide, and we can estimate the amplitude dependent frequency behavior as you can see in this slide here. We observe slight softening behavior followed by hardening, and this is expected because of the observed softening during the unloading case. Next, we consider the 2D model, and SICE was used to fit the results for the infinite friction case. The left plot here shows the SICE fit compared against the backbone curve that was simulated using Abacus. The right plot shows the amplitude dependent frequency plotted versus the displacement of the center of the panel. This is again showing slight softening behavior due to the unsymmetric unloading behavior. Okay, so here we're comparing the results from the SICE ROM on the whole 2D model against the results of the SICE ROM for just the 3D panel. Now the 3D panel, as can be seen on the plot here, shows more softening at low amplitudes than the 2D model. The main difference between these two models is the way the curvature was obtained. The 3D panel starts with a curved geometry, whereas in the 2D model, the panel is initially flat and then it curves due to the preload. So it is possible that this difference is what causes a difference in the amount of softening observed. But this is just a hypothesis and needs to be further investigated. Okay, so we looked at the results from the SICE ROM, and next we have to look at friction nonlinearity. As discussed earlier, the nonlinear force due to friction can be obtained by subtracting the backbone curve that you get for infinite friction and the backbone curve for mu is equal to 0.6 cases. This result is shown on the left. The right plot shows the Masing's rules that are applied to three arbitrary load amplitude. For each amplitude, the area inside gives the dissipation, and the secant gives the change in the stiffness. And now this can be repeated for every load amplitude. The figures here show the change in the stiffness and damping due to friction that is estimated using Masing's rules, using the method that was described in the previous slide. Note here that the linear stiffness, which would be the first coefficient of the SICE ROM, needs to be included when you're calculating the equivalent viscous damping from the dissipation. Now we need to combine the two models to estimate the overall effect on frequency and damping. For frequency, we consider the total stiffness as a sum of the amplitude-dependent stiffness due to SICE plus that due to Masing. Taking the square root of this gives us the frequency, and that is normalized to the linear frequency shown in the plot to the right here. Now, geometric nonlinearity does not cause any dissipation, so the damping estimate is directly that from the Masing model. With this, we get our latest estimates of the damping and frequency of the TMD benchmark structure. Now, what is the computational cost of doing this? The time above is the total CPU time that is taken by Abacus for the preload plus modal analysis and for the quasi-static analysis. A quasi-static analysis time that is reported corresponds to a static analysis step where the model was excited in the shape of mode 1 such that the center is deflected to 4.5 mm, that is 3 times the thickness of the panel. The 3D model, note that ran on 2 CPUs, so the total computational time was about 7 hours. Additionally, the NNM computation of the SICE ROM took about 25 seconds. As seen here, the 2D model is significantly faster than the 3D model, and the use of quasi-static analysis and ROMs makes this process much faster than having to do some dynamic analysis. Now, going forward, we still need to consider uncertainties due to material properties, surface roughness, and other such factors. Additionally, we need to verify the proposed reduced order modeling approach. There are different ideas for doing this, like using Abacus dissipation estimates, simulating a complete loading cycle in Abacus to compare. Dynamic simulations, however, these end up being highly computationally expensive. For example, 0.15 seconds of dynamic analysis on the 2D model takes approximately 48 hours. Next, we can use the 3D model for comparison as well as experimental results in the future. This slide shows the 3D model being used. As can be seen, we need a very fine resolution near the bolts in order to capture friction. So what we did was use the symmetry boundary conditions and only model half the entire geometry in order to save computation cost. In this presentation, we showed how the nonlinearity can be represented as a parallel arrangement of the SICE ROM and a Masing model, with QSMA plus SICE being used to predict the amplitude-dependent frequency due to geometric nonlinearity, whereas Masing's roots being used to predict the joint nonlinearity. We also showed how a 2D finite element model can be implemented to significantly speed up the nonlinear computations. With that, I thank you for your time, and I look forward to your questions and feedback at the conference.